Let's take a look at this standard Nernst equation problem. The cell potential for a cell not at equilibrium is equal to the standard cell potential minus 0.0592, and we can use that because we're at 25 degrees Celsius, times the log of Q. For this equation, we have 2 electrons being transferred. Where does that 2 come from? We've got a log. I'll tell you in just a second. We've got product, our only solid there. Our only aqueous or gas. And then we have to square our silver because we've got a 2 in our chemical equation over there. Now we need our standard cell potential. So we look at our half reactions. I've got silver plus an electron going to be silver. So that has a reduction potential of 0.80 volts. Then I have tin going to tin 2 plus 2 electrons. And when I flip the reduction potential for that from the chart, I get 0.147. Wait, did I say 7? 0.14 volts. Add those together, and I get 0.94 volts for my cell potential. You can see that as I saw that 2 in my balanced equation up here, that comes from the fact that I have to multiply this by 2 to get my electrons to cancel out, which is also why I have the 2 in the Nernst equation. So now, back to my Nernst equation, E is equal to 0.94 volts minus 0.592 divided by 2 log of products over reactants. We've got silver with a concentration of 1.3 times 10 to the negative second molar. Here's where the problem may be a little bit difficult. For whatever reason, they decided not to label this one with something that you really need. This is your concentration of your tin, right? That's your concentration of your tin. That's your concentration of your silver. It's really hard to work the problem without your concentration of your tin too. They should have labeled that. That's where they messed up. So that's the reason I'm putting that 1.8 times 10 to the negative second there. Another thing I nearly did is I nearly forgot to square my bottom number. So now let's plug that all into our calculator. Actually, let me do a little bit of simplification here too. We've got E equals 0.94 volts minus 0.592 divided by 2 times the log. And I'm going to simplify this term in here real quickly for us. That gives us 1.8 exponent negative 2 divided by 1.3 exponent negative 2 squared equals 1.065 times 10 to the second. Take the log of that. So that gives me 0.94 volts equals a negative 592 divided by 2 times 2.27. Whoops. Clean that up a little bit. All right, divided by 2 times negative 0.592. Oh, whoops, know what I did? And you're probably yelling at me. I dropped one of my zeros. It's 0.0592. That's what I get for working problems late in the day. Let me get that on my calculator before I hit equal sign here too. Well, holy moly. Well, okay, good deal. I think 0.94 volts minus what is now 0.060, which gives you 0.879 repeating, or 0.88 volts for your final answer. That's it.